Thank you. I should update my Adobe, I guess. I will be talking about bilinear complexity, which, as usual, is about a problem which I find interesting, but I haven't solved. So I will show you some proofs, but I hope that mainly the questions that I will raise will attract your attention. To motivate the question, I will start with a problem that some of you may have heard about before, and that is the sum of squares problem. The sum of squares problem is the following. You have a polynomial, which is the sum of xi squared yj squared over for ij coming from 1 through n. So the polynomial is sum of n squared squares, and the question is how many polynomials f1 through fk do you need so that the polynomial can be expressed as the sum of their squares. I will be referring to this polynomial, which will appear in this talk quite often as the sum of squares polynomial. Thank you for anticipating. It's without loss of generality. But there is no additional requirement. I emphasize that there are real polynomials, f1 through fk, and for those polynomials, they are without loss of generality bilinear. But in this phrasing, this comes for free, and there is no such assumption of f1 through fk. If you think about it for a few seconds, so the trivial bounds on k here would be n squared that k lies between n and n squared because the left-hand side already is a sum of n squared squares, and it's easy to show if you substitute for y 1 that you need at least n squares to write at least n squares to express the sum of squares polynomial. So those are the trivial bounds. Another bound, which is, I think, probably the most famous theorem about the sum of squares, comes through from Hrubes, who showed that the equality k equals n happens if and only if k is either 1, 2, 4, or 8. And this also explains the historical motivation for the study of this of the sum of squares problems, because this theorem of Hrubes can be interpreted as saying that
k is n if and only if k isn't 1, 2, 4, 8.
yeah. Okay, sorry. Yes, yeah, that should be n. Yes.
Okay.
Yes.
No,
No, you are right. Yeah. No.
It makes a little more sense that way.
Yes. Yeah. Sorry. Yeah. Here, k should be n, of course. If
right,
n
so
is equal. Yes. And this statement can be interpreted as saying that the real numbers, the complex numbers, quaternions and octonions, are the only normed division algebras. And this was the main motivation, I think, historically, for people to study the sum of squares and identity in the first place.
Why is n lower bound?
Well, you're asking about this part. So imagine what happens if you substitute for every y you substitute just 1. So then you are basically trying to write sum of xi squares as sum of squares in fk. Now, this basically, this in particular means that if you think about now the f1 through fk become linear forms in just xi's, and the property over the reals that you require is that if all of f1 through fk as linear forms are, it's actually related to the question whether we can assume the f1 through fk to be bilinear or not. But without loss of generality, those f1 through fk are bilinear in xy, which means that if you substitute for y, those fi's become linear. And they have the property that whenever all f1 through fk are equal to 0 for a given assignment for x, then the left-hand side must be equal to 0. So it must be, excuse me? You don't have to think about this Lancrova, but yeah. So you must have linear functions which have the property that if f1, so those are now linear, and you must have the property that if all of them are equal to 0, then x1 through xn is equal to 0 over the reals, which clearly means that k must be at least n, because the rank of the linear function must be at least n. Over complex numbers, this wouldn't work, but here we are working with real polynomials. So it is really easy, the first lower one. Yes, over complex numbers, you would have to use slightly more complicated argument than this, but actually, over the complex numbers, you would use you would have to think a little bit harder if you assumed bilinearity. Yes, I think so. Definitely over. If you add the additional assumption of, but I will get into the question in a moment. Well, okay. Over complex numbers, anything can be written as a sum of two squares. So if you want to work over arbitrary fields, you must add some assumption on what the FIs will be. The right assumption, an additional condition on the FIs. The condition that you would like to add is that the FIs are bilinear. And then this theorem holds over also over complex numbers, and I think over any field with characteristics different from 2. If characteristics is equal to 2, then this problem is again trivial. Yeah, but you lose a factor of 2 in this argument. There's a little bit more work that you actually need to do. Like the same argument that we now employed over the reals would sort of work over complex, but you would lose a factor of 2, which you have to compensate on elsewhere. There is more questions? There is another theorem of Radon and Hrubes which gives a non-trivial upper bound on the sum of squares problems, which is the following. So the trivial upper bound is n squared. You can actually improve it a little bit and to get again save a log factor and get an upper bound n squared over log n, which to my knowledge is the best upper bound on the sum of squares problem in this case. Yes. It's an explicit upper bound. It's a construction.
Cannot prove even non-explicitly upper bound better than square?
I can't.
Nobody knows. That's the best known.
This is basically the question. There are some upper bounds on this on K, which work in some specific cases and give you basically a factor of 2 here in some cases.
For example, little omega.
So for me, this question is mainly the question whether this K looks more like n or does it look more like n squared. You can improve a little bit, but morally still the upper bound is like n squared. For the lower bounds, the best lower bound we know are pretty close to n, and the main question for me is whether this number is n or is it n squared. There is a lot of research done when they study particle identities for fixed n, and they compute the exact k that you need if n is equal to 16 or some other number like that, but not much is known about like the asymptotic behavior of k as a function of n.
For example, some of these algebraic software packages to do these types of things?
No, it's very hard. Not directly, but the question has a similar flavor. It is a similar flavor like a tensor rank question, but I don't think there is a reduction in either direction.
If you replace the left-hand side by some more general form, then
That's also a good question. Yes, you can find an explicit polynomial which is basically where the x degree of the polynomial is 2 and the y degree is also 2, for which you can prove a lower bound of like n squared over 4. So there exists an explicit polynomial for which you can solve this problem. And yeah, that's a good point. Excuse me? It's artificially constructed polynomial, which I can show you after the talk, if I remember how it works. And there is a paper about it. The only lower bound which works asymptotically and gives something superlinear is the following. But in this lower bound, so that's a work we did a long time ago with Avi and Amiri Hudev, where you explicitly require the polynomials fi's to have only integer coefficients. So in this case, you can prove that k must be at least n to the 6 over 5. So it is a superlinear lower bound. It can also be noted that the upper bound here is achieved by polynomials with integer coefficients. For rational coefficients, the same. No, no, it's not. We don't know.
Right, because I mean, your bound doesn't depend on the magnitude of these integer
No.
coefficients.
Well,
Right. Yeah, because you can't scale the other side too.
that's yeah, that's
Yeah,
one.
because you can't. Yeah. You can't just scale both sides.
So this is the sum of squares problem. There are a few more observations that one can make. So this is the state of art, I think, basically about what is known about this question. The question, the main question for me is not to know what is the exact value of k, just roughly where are you closer to n or n squared. There are few more observations to make. One of them is, as was anticipated before, you can without loss of generality assume that the polynomials fi are bilinear in x and y. So in particular, they have always degree 2 and are bilinear in x and y. And if you impose this additional restriction on the fi's, the problem can be stated over an arbitrary field. Just to avoid trivial solutions, because over complex numbers, if you don't add this assumption that everything is a sum of just 2 squares, and so adding this assumption on fi's, you can ask the same question over any field, but you should probably avoid fields of characteristic equal to 2, where the left-hand side, the sum of squares polynomial, can be written as just 1 square, which is equal to c. So the problem here would be non-trivial for any field of characteristic not equal to 2. Well, I'll answer the question on the next slide. Mathematicians are interested in this because they are interested in constructing normed division algebras and things like that. So the left-hand side is interesting historically. Now, for computer scientists, usually you don't care just about this specific polynomial, but it would be enough for you to construct some other explicit polynomial for which you can prove quadratic lower bound. But this polynomial seems like a particularly good candidate. The next problem that I would like to mention is a modification of the sum of squares problem, and the modification is the following. So instead of writing the sum of squares polynomial as a sum of bilinear squares, you want to write it as a sum of products of bilinear functions. So the sum of squares problem arises when you require g1 to be equal to f1, g2 be equal to f2, etc. So this is a relaxation of the sum of squares problem that we saw before. And in this case, the motivation for studying the modified version of this problem is the following. That's a work that we did with Avi and Amir again a long time ago here in Princeton. That is, if you can prove a superlinear lower bound on this modified version of the sum of squares problem, then you get exponential circuit lower bounds for non-commutative arithmetic circuits computing the permanent. So now to answer your question, so here the same argument will work if on the left-hand side you have any explicit polynomial of the of roughly the same format like the sum of squares polynomial. So in this case, if you solve this problem for any explicit polynomial, this will be fine.
So what if you require, say, integer coefficients here? Is there any sort of, is there a sense in which it
no, but there are, but you are pretty close to getting an getting one. Like here we can't prove anything about the, even if you require the f, wouldn't it imply the lower bound on the on permanent with integers? No, I think you need to divide by 2 at some point, so it wouldn't go through. Like here, if you could prove it over rationals, you would be really happy. Like in the original formulation of the sum of squares problem, even if you prove a lower bound there on k over reals or rationals, it gives you nothing in terms of complexity. In this modified version of the problem, if you work over rationals, you get a lower bound over rationals. Now I'm not 100% sure whether you really need rationals or whether integers would be sufficient.
Well, there's some bounded fractionality.
Yes. In this case, one advantage of this formulation is that in this version there is not much of a difference between complex and reals.
So what about in the original problem?
As far as I know, that there could be, but I don't see why there should be. But over complex and reals, there's the only thing you lose is a factor of 2 when moving between reals and complex. For reals and rationals, I don't know, but I would guess that it shouldn't matter too much. Mm-hmm. Yes. Not for this problem.
So is this problem known if there's an explicit one or an explicit nothing? Ah, oh, okay. No, but that's conditioned on the left-hand side being this.
Over complex, for example, you can have over, if you work over complex numbers. So in this problem, I will allow myself to work at the field of my choice over complex numbers easily. You can, if n is equal to 2, you can write it as a product of just 2 bilinear forms. Because x1 squared plus x2 squared is equal to x1 plus ix2 times x1 minus ix2. So there, over complex numbers, you can save a factor of 2 actually in this problem. So this is and now over complex numbers, this version of the problem is basically equivalent to the original version of the problem of the sum of squares problem, where you may or may not lose the factor of 2. So Morally, I think for me, this question is more robust than the sum of squares problem. And also, there are this implication which I mentioned first is that if you can prove a slightly superlinear lower bound for k, then you get an exponential lower bound for the permanent. That was the original motivation why we started studying this problem. And I should emphasize that we know basically nothing about this problem.
So for the sum of squares problem that you mentioned on the previous slide, what is the fielding about what the right answer should be? I mean,
I believe that it should be the n squared over log n is optimal. Maybe also here.
well,
Yes.
this question I don't. I mean,
No, but if you allow that left-hand side to be anything, you can show that first, right? Non-explicit.
Yes, of course.
Just doesn't imply
Well, it will give a lower bound on non-explicit. No, it works for. I think the question was by counting argument, you can show that there exist polynomials on the left-hand side where k will be roughly n squared, which gives you that there exist polynomials which are hard to compute in the non-commutative setting. So you'll get like a non-explicit lower bound for arithmetic circuits which you don't want. Here you really need the left-hand side to be explicit in some sense. Yeah. Okay.
I'm taking the time of questions off your lot of time.
the most questions I've seen in 2 slides of the talk. I guess we could have asked questions on the title slide too.
Yeah, the title slide, you could have asked what's bilinear complexity, for example. That would be like a good way how to pick it. Oh, yes. No, thank you, sir. Well, another way how to formulate the problem one is you can replace you can reformulate the question in the following way. You can just ask how many bilinear f1 through fk do you need so that you can place the sum of squares polynomial in the ideal generated by f1 through fk. This should be easy to see because in this expression over here, if you can place the sum of squares polynomial in the ideal of f1 generated by f1 through fk, then you can express the sum of squares polynomial in this way, where g1 through gk are some polynomials. Then by comparing the degree on the left and the right hand side, you will see that without loss of generality, actually the g1 through gk will be bilinear. So this is an equivalent formulation of the original problem. Yes? And now, if you formulate it this way, so I think one relatively naturally asks the following question, and that is, instead of thinking about the sum of squares of the powers of xi, yj, then simply ask how many bilinear polynomials you need so that you can place every term individually into an ideal generated
So
by.
isn't this similar now to asking whether any, I mean, it's asking whether you can choose any, the left-hand side with any sort of linear combination instead of summing them up and still express it, right?
Yes, yes, that's yes.
I mean, it's asking for.
But you
Same idea. So
yeah, it's the yes.
Right,
Like-
but I'm asking if there's a certain, I mean, when you've gone to problem 2 now, it seems like you've also added an element of inexplicitness to this because, if you show a lower bound here, what it sort of means is that, no, not just for the sum over ij, but for, wait, no, what's the order of quantifiers?
first,
works
yes.
for all I and
Oh,
j.
yeah, so
Yes.
yeah, if you could do this, you could do that.
Yeah,
Roll
yeah,
down
yeah.
here with much
Yeah.
easier.
Yes.
I agree, but I'm saying then,
Do you know how to disappear this thing?
yeah, you just move the cursor.
Yeah, like this.
No, on the laptop.
On the laptop, you should move the
Thank you. So, like easily you can see that this k prime from problem 2 is greater or equal, there should be greater or equal sign, not a bigger sign than k, simply because the sum of squares polynomial itself lies in the ideal generated by the squares of the variables. So if you believe, as I do, that the answer to problem 1 should be roughly n squared, then the answer to problem 2 should be also n squared. And here you are trying to place n squared things into the ideal. So you are reasoning, instead of about one polynomial, you are reasoning about n squared polynomials. So it seems that proving n squared lower bounds should be easy, simply because you have n squared polynomials to begin with. And I thought that it should be easy to prove that here the answer should be n squared. And for this problem, we don't even know, or I don't even know whether one can save this log factor. So maybe for this problem, the answer should be like n squared sharp or n squared over 5 or something like that. Yes. I made it easier for myself, but more difficult to satisfy. Yes, but it was for the sum of squares problem. It wasn't for the the sum of products of bilinear forms. Yes. So this problem should be much easier, or at least it appears much easier than the first problem, but there is very little I can prove even about this modified version of the problem. I think I'll show you some really elementary lower bound and an upper bound. Yes. Yes, that's also a good question. Then the answer is 2n minus 1. For 2, yes. For 1, for 2, yes. For 1, I don't think we...
No, but it's now the radical. Oh, you mean replacing from this equivalently version now with the radical of the ideal, right?
I would have to think about it, because now it matters whether you are working over complex or over reals. So, no, so okay, if you replace it by the radical, you get something either 2n minus 1 or something pretty close. So the upper bound, you will get an upper bound which is really small. So that's one, I think, one reason what makes this question difficult, that you cannot argue about radicals, you cannot argue about varieties, because then you get upper bounds which are really low. Yes. Yes, so like the algebraic technique only about arguing about roots of polynomials in principle cannot give you anything which is good. Another option is, of course, that maybe you could construct some nice upper bound on this problem, because like often you would like to construct an upper bound by induction on n, and so if you have the right inductive assumption, often it happens you get a better bound. So if you are proving a stronger upper bound, maybe it will be easier to construct the upper bound, and thus showing that the answer to problem 1 is something closer to n than we originally thought. But the best bound you will see on problem 2 will be something between 2n minus 1 and n squared over 2. So at least my knowledge of problem 2 is extremely limited. Let me give now a general definition of what bilinear complexity should be, which is basically what you would expect when looking at problem 2. So I'll assume that we are working over some field. Nothing what I will say will depend on the field, so just imagine what field you like. You have variables x1 through xn and y1 through yn, and you have a set of polynomials in those variables. And you define the bilinear complexity of the set of polynomials G as the smallest k, so that you can find bilinear polynomials f1 through fk such that G lies in the ideal generated by those polynomials. Of course, it may happen that no such k exists. If you assume that G is just a linear polynomial in x, you can never express it in this way. So, but I won't care about those cases. I will just say that the bilinear complexity is infinite. So in the first problem, basically what I was asking is to estimate the bilinear complexity of the sum of squares polynomial, and in the second problem, which was supposed to be easier, to estimate the complexity of squares of variables, squares of products of variables. This is a general definition. So so far we saw G consisted of polynomials which were degree 4, had the x degree was 2 and the y degree was also 2, but I have no such assumption here. It's just a general definition. Yeah, well, that's true. So this is a...
Well, he's defining it this way, right?
Yeah, this is just a definition. Then one can have a discussion whether the definition is good or bad, but I like the definition. The basic properties of the bilinear complexity, that you can see that if it happens that it's not infinite, so that G can be written as can be placed into the appropriate ideal, then the complexity is at most n squared, because you just take the products of all the variables. You can also see that if G2 is contained in the ideal generated by G1, then the complexity of G1 is at most the complexity of G2, which basically means that, yes?
In the first item, you assume that polynomials are all equal to?
No, no. There is no, okay, I should emphasize that.
Just all the xi, yj, that's containing the variable.
Yes. I should emphasize there is no restriction on G in this case, just an arbitrary set of polynomials, but you care only about polynomials in which every monomial contains x and contains y. Otherwise, the complexity is infinite, and so every monomial contains xi times yj for some I and j. So it's sufficient without loss of generality with f1 through fk to be just xi times yj. There are n squared of those. The second property means basically that the bilinear complexity is actually not the quality of a set of polynomials, but rather of the ideal generated by the set. So you can as well reason about ideals instead of by the sets generating the ideals, and you can move freely between the generators of the set. Yes, exactly. Yeah, that's the point. So if you have G1, G2, we generate the same ideal, then the bilinear complexity must be the same. Yes. Yeah, probably could add a few more properties there. As I said, the problem 2 that you saw, which was the question, what's the bilinear complexity of squares of products of variables? I know very little about it, and then one goes on to generalize the problem as far as he can till he can prove anything. So there will be another set of polynomials that I will be thinking about, and that's the set QMN, which is just the set of mth powers of monomials xi, yj. And since the amount of things I can prove about sets of this form is relatively limited, I'll introduce one more set, and that's the set Q1.5f, where you have, which is the set of monomials of the form xi, yj squared. And I will tell you something about the bilinear complexity of those sets as they depend on M. one thing you can see, of course, that the bilinear complexity is decreasing as m increases. So proving lower bounds is getting harder and harder as m is getting bigger and bigger. And the question that I will address now is that how roughly what roughly happens. So that's the first theorem. So the first point of the theorem is trivial, and if you think about m is equal to 1, then the bilinear complexity is n squared. And that's, I think, the only tight bound that I can prove in this context. And that's simply because you are trying to put the set Q1n, which is just the set of xi, yj, where ij ranges over 1 through n. You want to express it as, yeah, it's just linear combinations of bilinear polynomials. So the rank of the polynomials in Q1n is n squared, as you can see easily, and so the bilinear complexity will be also n squared. So this is a very simple bound. The second point is that for every n there exists an m which may be potentially very large, such that the bilinear complexity is 2n minus 1. And this is related to the question that Zev asked, and this basically arises from taking not the ideal, but the radical of the ideal instead. I will give you an outline of the proof in a moment. So if you allow yourself m to be really big, the bilinear complexity will drop and become linear. This, unfortunately, is a little bit frustrating in this setting. So the intuition sort of that you have n squared things, and therefore you should be able to prove n squared lower bound sort of doesn't apply, because it does really matter what are your n squared things that you are working with in the first place. And it also means that techniques based just on say algebraic geometry, or if you argue about roots of polynomials instead of the ideals, can't give you bounds which are better than linear. And the third thing is that actually the lower bound is the upper bound from the second part of the theorem is sort of tight, and that is for every n and m you can never do better than 2n minus 1. The proof here is the proof of 2 and 3 is relatively simple, and well, at least part of it is relatively simple. So call a bilinear map from, and now I should emphasize that I didn't assume that the field F is algebraically closed, but now let's think about the algebraic closure of the field, and call a bilinear map from Fn cross Fn to Fk non-singular if for every x and y, if the image of x and y is equal to 0, then either x or y is equal to 0. So that's a definition of what does it mean to be a non-singular bilinear map. Simple observation is that if Qmn is contained in the ideal generated by F1 through Fk, where those Fi's are bilinear, then those Fi through Fk are actually a non-singular map. This is because if you recall, the set Qmn is simply a set of all polynomials of this form, xi to m, yj to m. So if all F1 through Fk vanish at some point, then all of those polynomials must vanish at that point, which means that either all of the xi's are 0 or all of the yj's are 0. So if Qmn is contained in this ideal, then the bilinear forms give you a non-singular bilinear map. That's one observation. The second observation is that if you have such a non-singular map, then there must exist an M such that QMN is contained in the ideal generated by F1 through Fk, which is an application of no-Sternsatz. So again, if all F1 through Fk vanish, that means that all xi times yj must also vanish by the definition of the non-singular map, which means that by no-Sternsatz there must exist some power of xi yj which lies in the ideal generated by F1 through Fk. So that's an no. But I'll be happy if you tell me what you mean after the talk. So now the question arises, what is the smallest case so that you can construct such a bilinear map? And it is easy to construct it explicitly for k is equal to 2n minus 1, and it's really easy, and I'll show you in a moment. But this already gives you that there exists an M such that the bilinear complexity of Qm is equal to 2n minus 1, which was one statement of the theorem. And in a more sophisticated manner, you can show that 2n minus 1 is actually the best possible answer you can get in this case, which then implies the lower bound from the theorem. I'll show you the easy construction of the non-singular bilinear map. So consider matrices A1 through AN, which are matrices of dimension n times 2n minus 1, which look as follows. A1 is just the identity matrix followed by zeros. A2 is a matrix which has zeros in the first column and the identity matrix next to it, and zeros elsewhere, etc. So the matrix AN will have the identity matrix at the end and zeros elsewhere. So those are your matrices A1 through AN, and now define the map fxy, where x and y are now vectors of variables, as x1, xn. This is now a vector times a1, y1 plus an times yn. So this is a vector of variables. Now this is a matrix which is linear in y's, which has dimensions n times 2n minus 1. So this indeed gives you a list of 2n minus 1 bilinear forms. The reason why you define those matrices this way is that if you take any non-trivial linear combinations of those matrices, the rank will be always n. So if you choose any possible coefficients for y1 through yn, as long as at least one of them is non-zero, the rank of this will be always n. So if you now assume that f of xy is equal to 0, then you must have that either x is equal to 0 or y is equal to 0. Because if y was not equal to 0, then this matrix is a matrix of rank n, but then it implies that this vector must be equal to 0, because this whole product is equal to 0. So that's a simple construction of the non-singular map. But one aspect of the construction is that the bilinear map actually uses only 0, 1 coefficients, so it can be constructed in the field F and not in the algebraically closed extension of F. Yes? Yes, yes, exactly. So basically, the lower bound here was proved, I think, independently by Smith and Sylvester. Sylvester proved the lower bound by showing that any set of matrices which has the property that that every non-trivial linear combination has full rank, then the longer side of the matrices must be at least 2n minus 1. So this is basically equivalent formulation of the problem. He proved it over complexes. Smith then proved it over any algebraically closed field. It's important now that we are working over the algebraically closed extension. The problem becomes much more difficult if you were stating the same problem over, let's say, reals. Then becomes much more complicated. Excuse me? Yes. No, unfortunately not. It's essential, in this argument, it's essential that you work over algebraically closed extension. Yes, but yes, but here my polynomials f1 through fk lie in reals, but I need to take the variety to contain the complex numbers. Like if you are talking about positive Stellensatz and those versions of no Stellensatz, that doesn't seem to give anything at all. Now, I'll show you, I will state a different theorem which concerns this sort of a hybrid set, which is defined in the following way. And for this, and this is the only non-trivial case for which I can prove non-trivial lower bound, for this one can prove that the bilinear complexity is at most this n times n plus 1 over 2. This is not very interesting statement. The only reason why I mention it is that the answer is not simply n squared sharp, that you can save at least a little bit. But more importantly, here one can prove that the bilinear complexity of this set is at least n to the 1.5. The FIs are bilinear. Oh, bilinear in x and y. Yes, every. Oh, yeah, that's what you are talking about. Yes, yes, that's basically the point of the lower bound. Yes, that's one reason why you choose this set in this way. That actually the GIs will depend only on y. That's one way how you save it. I'm not sure how much. The proof is quite simple, as Zev already is guessing how it's going to go. But so let us assume that for every I and j, xi yj squared lies in the ideal generated by g1 through gk, where those gi's are now fixed, and they of course don't depend on I and j. And now define the two following sets, and the set Vd will be all homogeneous polynomials of degree d just in the variables y, and let Wd be the homogeneous polynomials of degree d which lie in the ideal generated by y1 squared, y2 squared, and yn squared. So the first claim is that for every d, this k can be lower bounded by n times the ratio of the dimension of Wd and Vd minus 1. Why? This is because if we define one more set, ud, which now remember then that the polynomials in Wd, they depend only on y, but let us now lift it to polynomials which are of the form x1 times f1 plus x2 times f2 plus xn times fn when fi lie in WD. The first thing that you will note that the dimension of this UD is n times the dimension of WD, because those are n. I'm now treating the all of those sets as vector spaces over the reals, or over the underlying field. So the dimension here is n times the dimension of WD, because you have just n distinct copies of f1 through fn. Second thing is that this UD is contained in the ideal generated by G1 through GK. This is simply because that UD lies in the ideal generated by xi yj squared, by definition. A third thing to note is that by restating this definition, for every f, you can find some h1 through hk such that this equality holds. As Zev noted, without loss of generality, you can actually assume that those h1 through hk depend only on the variables y only, and the degree will be d minus 1. This is simply by comparing the degree of f on the left-hand side with the degrees of the terms on the right-hand side. But this also means that you can think about h1 through hk as simply vectors of their coefficients, and you are getting a linear map from k copies of WD, or from k copies, you are getting a linear map from k copies of VD minus 1 into the set, into the vector space UD, which means that the dimension of UD is at most k times the dimension of VD minus 1. Remember that those G1 through GK are fixed, so this indeed is a linear map. Every h1 through hk defines some polynomial f, and it's actually a linear map from VD minus 1 to the k to UD, which proves the first claim. Well, and the second claim is now, of course, one wants to now maximize the dimension of WD over the dimension of VD minus 1, which is relatively simple. The only, I think, surprising thing about this proof is that it does give something non-trivial, because if you try feeding for D some constant, you get nothing. If you try feeding for Dn, you also get nothing. But if you feed for D is roughly square root of n, then you will get the ratio of the dimensions of the two spaces roughly square root over n. This is a simple computation, but let's just note that VD consists just of polynomials of homogeneous polynomials of degree D in n variables. So the bases are simply all monomials of degree D, and the dimension is this number. The dimension of WD is, again, the bases are all monomials, homogeneous monomials of degree D, but you are removing multilinear monomials because you want every monomial to contain a square. So the bases here are all monomials of degree D except those which are multilinear. And there are n-choose D multilinear monomials. So those are the two quantities that you are playing with, and the rest is just a computation, which you can look at. Yes? No, unfortunately not. This computation cannot give you n. Maybe there is some. well, so we are because no, if d was a small constant, then you get
Oh, sorry. The right hand side then will be.
yeah, yes. So like if d is a constant, this goes in the limit goes to 1. You don't get even a constant factor. And so you must choose something which grows, but it also shouldn't be too big. And d is equal to square root of n is the optimal choice, I think. Excuse me? I sincerely hope so, but yes, I think yes. Like maybe you could earn, you could be saving on constants, but I don't think you can get anything better than square root of n. So this is just a computation, but basically, if you choose d greater than square root of n, then the term n plus d minus 1 choose d will become constant times n choose d bigger, which you do by substituting and computing. So eventually, the ratio of the dimensions, which is this thing, will be this expression, because this term is, let's say, twice bigger than that term. So you can as well forget about this term, and it's just the ratio of this against this, which equals that thing, and which means that if you choose d around square root of n, you will get like n over square root of n, which is square root of n, which proves, yes, oh, larger than 1, yes, yes, that's important. Yes, sorry. Yes, well, larger than 1, yes. So just to sum up the theorem, which is not difficult, is that first of all, you have by claim 1, you could estimate k by n times the ratio of the dimensions of the two spaces, and if you choose the degree appropriately, the ratio will be roughly square root of n. So the lower bound you get is roughly n to the 1.5. And this basically sums up all the things that I know about bilinear complexity in this context. I don't know, this sort of argument doesn't work even for the set Q2n, which is the sum of squares of products of variables. It doesn't seem to get even a constant factor. So it's not clear what happens in the situations that one would really care about. No. The problem is that you are thinking about the ideal generated by bilinear polynomials, which have degree 2. The farther you get from that degree, the worse things get. But for me, the surprising thing is that the things get pretty bad already when you are thinking about degree 2. At least when you are trying to apply this sort of a technique. And so I'll end up with questions, open problems. So the first one is to estimate the bilinear complexity of sum of squares. And this is the really interesting question that would have implication in circuit complexity. And this is the most interesting question in this context, I believe. Or if you want, you can replace the left-hand side by an explicit polynomial, and that would also be very interesting, and that's also not known. The second problem is the weakened version, where you are thinking about bilinear complexity of squares of products of variables. And for this case, the best lower bound we saw was 2n minus 1, and the best upper bound was like n squared over 2. And I don't know anything better than that. The third problem would be if you can't prove such a nice lower bound, then maybe there is at least some non-trivial construction that can decrease the bilinear complexity. And finally, the question is, you will know that the questions are in like decreasing order of interest. So the final question will be, how does the complexity of this set of polynomials depend on m? So we saw before that if m is equal to 1, the complexity is n squared. And if m is this 1.5 thingy, then it's n to 1.5. But already for m is equal to 2, the best bound you get is 2n minus 1. So the complexity somehow decreases with m. It will eventually reach 2n minus 1, but it may reach 2n minus 1 like smoothly. You move from n squared to 2n minus 1, but it may also happen that it drops sharply to 2n minus 1 already for m is equal to 2, which I don't know whether this can happen or cannot happen. So thank you.